My name is Vijay Ganti. I am part of VMWare, and I head up product for Security Products Group, as well as run the machine learning AI research team. It's a very unique role in many ways. Machine learning research is not usually part of product team, but I get the benefit of doing that. There's a natural advantage to that. Our research is focused exclusively on capabilities that we can add to our products. So that gives us pretty unique insights into what works and what does not. A quick question before I get started. How many of you are interested in the cyber hygiene part of the talk? Okay, a few. And how many are interested in the AI ML part of the talk? Okay, I guess it's equal. Just wanted to get a sense of that. So what I'll do is there are three things I'll cover today. Talk about how we see information security, what is the state of the union, what are the issues and challenges that we face first, what are the elements of solutions to those challenges, and then I'll talk about what is the role of AI in that solution. And I'll try to cover some history of AI as well, because I think that's pertinent to setting right expectations. So let's get started. There was a couple of years back, VMware did research on the state of information security. There are a couple of things that stood out to us. The first was the bad news, which is the IT spending, the growth in IT spending is plateauing with time. Doesn't mean we have to do less. We in fact have to do much more. We need to support many more applications, many more devices, many more deployment models. So that's the bad news. The good news for security teams was that security as a percentage of IT has been growing very, very robustly. So it seems like we are focused on investing in security. Right? So that should mean a lot of good stuff for us. Let's see where that money goes. So we looked at all this money that's spent on security. It's close to $80 billion. It goes into a bewildering array of products. I've been in security for a while. I can't tell you really the difference between categories. Forget the specific products. So this has to be a problem. Complexity is bane of security. I'm pretty sure all of us face this. And the natural result of this, the worst of all news, actually is that red line that we saw. So the only thing that's exceeding the growth of our security investments is the cost of breaches, right? So the cost of breaches have gone up to $600 billion actually last year. I'm told it's close to the drug rate, just to give you a sense of perspective, right? So something's not working. We looked at it and said, more money, more tools is not necessarily going to be the answer to this problem. How many of you have faced this issue already? Many tools, but still no hope of security. I guess none of you, okay. We're all secure? Okay. That was a rhetorical question, that's fine. So we kind of looked back again at VMware. This was a 2-3 year exercise. Looked at all the products and what are we doing as an industry? How are we serving our customers and what's going wrong? So if you look at this is just a simplistic breakdown of a typical attack, right, into 4 steps. Infiltration, propagation, extraction, exfiltration. Right? It's more complex than this, but we use this framework. The first observation we had was that all the $80 billion of security products we have are focused on preventing infiltration, right? And we underinvest in resilience. What this means is if one server is compromised, everything is compromised, right? So keys to one server is keys to the kingdom. Now, this is wrong at many levels, right? First is this. In a cloud and mobile world, really, trying to stop people at the gate, it's just not going to happen, right? I mean, we're just watching the wrong thing here. There are other problems with this. The second problem we have is we are not leveraging asymmetry. What this essentially means is that the attacker actually has to succeed in every step of an attack to succeed, right? To get away. So all we have to do is break one link in the chain to thwart his attempt. But if you're trying to only stop infiltration, you're not leveraging this asymmetry that benefits you. The second thing is that we're actually not using the home court advantage. I don't know how many of you have seen Home Alone. As a kid, I just loved that movie. Macaulay Culkin essentially used the home court advantage. He knew his house better than thieves, and he used this to his advantage. When we just focus on preventing infiltration, we're not using that home court advantage, right? There's only so far an analogy can go, so I would ask you to refrain from extending it too far, but that gets the main point, right? The second thing we saw with existing products that are focused on the latter half of kill chain is that we overinvest in chasing threats and we underinvest in shrinking the attack surface. Now, just to give you a sense of how bad this is, there are 500 million variants of malware out there today, millions getting added every day. You take fileless attacks into account, you're talking about billions and ever evolving. Chasing threats is an unbounded problem, right? It is reaching a point of diminishing returns for us. On the other hand, we don't invest in shrinking the attack surface enough. Things like segmenting or micro-segmenting your network, things like application control. These are things that we don't really invest in at all. And it's not just us saying this. Gartner has this pyramid that talks about control workload protection controls, right? So what kind of cloud workload controls should you have in place? So in this pyramid, the most important controls are at the bottom of the pyramid, right? And the least important are the top of the pyramid. The foundational at the bottom, least critical at the top. Notice what is at the top? AV. The last thing you should do. We don't do that, right? We just don't do this. On the other hand, in the bottom segment, they say you should do things like application control. You should do things like segmentation. These are things that are cyber hygiene. This is what you have to do. We underinvest in this. And the way to think about this essentially is the top part of the pyramid. By the way, there was a very nice animation here which got spoiled because I moved from Mac to Windows, as you know. But essentially, the top part of the pyramid is your residual cyber threat, residual risk because of cyber threats. The bottom part of the pyramid is a set of things that ensure you have cyber hygiene. So you have to get that right? So you should think about your security stack essentially as two sets of controls, one ensuring cyber hygiene, and whatever is the residual risk because of threats is addressed by other set of tools. That's the way to look at it, right? Now, there's a third problem we noticed with the products. Most of our security controls are aligned with infrastructure, and they're actually not aligned with applications and data. What does that mean? Applications and data are what we are trying to protect. Infrastructure like network and endpoint are the places we are trying to protect from, right? And the last time these were closely tied to each other was when you had monolithic applications, right? You had a single application sitting on a single machine, and infrastructure was a proxy, a good proxy for your applications. But that's not true anymore, right? A good analogy of this, actually, is imagine you were trying to protect your company and all the employees in your company. Let's say they were all in one building. There was an easy way to protect them is to put a guard at the door, right? That's it. So you protect your building, put a guard at the door, and you protected all your employees. And moreover, it's very easy for that guard to detect anything anomalous in the lobby. It's very easy to spot any odd person out. But now imagine your company actually changes to this. You have offices in different buildings. And moreover, that one building actually has people from other companies, so multiple tenants out there. Now think about that guard. A, he's definitely not protecting your office and your employees because they're in other buildings. Secondly, it's very hard for him or her to detect something anomalous in the lobby because now there are many, many different people out there, right? This is what has become for our application. This is the de facto standard. Your apps are now distributed all over. The web tier, the app tier, DB tier, storage, everything is in different places. the traditional perimeter controls tied to your infrastructure don't work, right? Now, let's look at how this affects in case of our networks. Today, if you look at networks, they're extremely flat. How many of you have just largely two segments, external and intranet? Do you have more segmentation than that, a little bit more? Yeah, so I think some companies essentially have gone to segmenting by infrastructure components, like all web servers in one segment, all app servers in one segment. But they don't segment necessarily by application boundaries, like SAP or your payments account receivable system. They just don't do it that way because components are all over, right? Now that's a problem, primarily because if you are commingling different applications in the same segment, one of the web servers is compromised, everything in that segment is compromised. And because you have to allow applications to talk to each other, essentially everything is compromised. The hacker can traverse this just using the traditional pathways that are available already. This is security theater, basically. Just doesn't work. Look at compute. This is again an area where you're not shrinking the attack surface. A general purpose computer is an extremely complex thing that can do millions of things, right? But what a particular application uses is a very small subset of those capabilities, okay? But what attackers do is leverage all those 999,000 other capabilities which are not being used by that application as attack surface. They essentially rootkit the operating system, compromise processes that are running needlessly. Those are the things that are expanding the attack surface, right? And this creates a significant expansion of risk. What we did at VMware based on these things, these ideas of first not just focusing on preventing infiltration, focusing on actually reduction of shrinking of the attack surface, and lastly, being able to provide the application context and focusing on app and data. We said there are two things that we should be able to do. First is we should build a secureable infrastructure. Now, I didn't say secure infrastructure, I said secureable. This is not just infrastructure with low vulnerabilities. That's not what it is. It is something that understands the application context. It understands what is the application running on that infrastructure, what's its intended behavior, and is able to provide those boundaries and use those boundaries to lock down the policies on that particular infrastructure, right? The second thing it does is that it's automatable in terms of response. So your traditional responses are pretty much block and allow, right? And that is extremely draconian. Often the cure is worse than the disease. How many of you have actually blocked policies that automatically block certain applications? Okay, far and few, right? Extremely dangerous doing that. You would probably do it for very critical applications. We can provide, with infrastructure that can have much more granular and much less draconian responses, right? The second part of our strategy was to expose those application boundaries to an integrated ecosystem. So we should not be the only beneficiaries of that application context, and we should serve it to an ecosystem of partners, right? So those were the key things, allowing us to deliver cyber hygiene and shrink the attack surface, at the same time handle residual risk through this integrated ecosystem of partners. That was a broad strategy that VMware has. Now, what does it have to do with virtualization? Like, why should we be doing anything about it? So this begs just thinking a little bit about what is virtualization. Virtualization is nothing but a ubiquitous abstract layer that provides a map of sorts, right? So on top of this layer is the application and data. Below it is the infrastructure, network and endpoint. So all the virtualization layer is doing is it's keeping a map of every point on the layer on the top with a point on the layer in the bottom, right? That's what it's doing. As they change, the virtualization layer stays updated with that. That gives us 3 or 4 unique properties, right, that allow us to deliver this. First, it understands the application context. It knows where it's running, what it's running. It clearly knows that. The second thing it has is an isolation property. Now, what happens with the traditional endpoint controls is that if the operating system is compromised, what do the attackers do? They'd go and disable the agent, tamper with the agent, because it's operating in the same security domain. On the other hand, if you have controls in the network, they have great isolation, but they have very little context. For instance, you would not know which process specifically is making that network connection. You would know virtual machine, but you wouldn't know which process is making that connection, right? On the other hand, the virtual isolation layer, we call it the Goldilocks zone, kind of has not too hot, not too cold. It has both context as well as isolation, right? So we said we can get that property. The third thing we do is, the property is one of being able to automate responses, which I already talked about. So that's why virtualization is relevant. Let's look at what that would actually do to the charts that, to the slides that I showed earlier. So if you were to go back to a network, with virtualization, what you can do is essentially draw perimeter across the application components. So this is a virtual perimeter, right? It's almost like there are no laws of physics don't apply to this, right? Because we're not tied to the infrastructure in this case. Now what that does that do? If a web server for a different application is compromised, you still cannot compromise the other application because there's a virtual perimeter around it. And you can actually augment that perimeter with your traditional network controls, but bound it to this particular perimeter. So you don't commingle policies. Your policy implementation stays simpler, and you actually get better security. This is one way of shrinking the attack surface. If you go back to compute, the same idea. Essentially, instead of letting everything run on a compute node, you only allow what is relevant for that specific application to run on each compute node. And that way, you essentially take away a large part of the attack surface. Now, this doesn't solve all problems. Just remember, you're still looking for a needle. It's no longer looking for a needle in a haystack. You're looking in a few pieces of hay, right? So you still have to look for the needle. Anybody who tells you that they can solve everything, I guess, I mean, maybe they can, but we won't make that claim ever, right? In a nutshell, I think the big shift that I think we have to make collectively is that our focus has been inordinately on chasing bad, whereas the focus should be on ensuring good. And they are complementary, but again, it's the amount of focus that we need to put on each of these, right? So this is all fine and dandy, right? So how does AI play a role in all this? Now, I want to give you a brief history of AI. How many of you are very well versed with AI developments? Okay. Okay, so I think it's a good reason to just walk through, the history of AI. How many of you think AI will solve all our problems from a security perspective? Very few. How many of you think it can help? Okay. Okay, I'm going to say, okay. How many of you think it can help more than 50%? Okay, that's interesting. Yeah, so I think we should make our judgment after this talk as well. I don't have a very strong position. I'll share with you what I think reality is, what we are seeing, but we'll get to that. So first of all, AI is not new. In 1950, we had the Turing test, right? Alan Turing essentially said, by year 2000, humans, or actually bots, would be able to fool humans when chatting with them over a text-based conversation for 5 minutes that they are actually humans, right? So they'll be able to fool humans into believing that the bots are humans. And they'd be able to do it 30% of the time, right? So you'll be able to tell 70 out of 100 times that they're bots, but 30% of the time, you would not be able to tell that it's a bot on the other side. And he said by year 2000, by the way, right? And then the word AI was born in 1955. Then a lot of stuff happened. These are all projects happening in academia. And by 1966, we had a bunch of stuff, but nothing really came out. And there was an AI winter. And I'm told, this predates me, but I'm told the excitement in AI at that time was palpable. And some say, arguably, it was more than what we see now. But it didn't hit anything, right? It just hit winter. This winter lasted for a while. The only debate is whether it was 2 winters or 1 winter, but it lasted for around 30 years. There are a few things that happened in between, but not very significant. Fast forward to 1997. Deep Blue beat Kasparov, right? After a long, long time. Now, some argue, there's a school of thought which is called the AI effect. Essentially, these people believe everything that's not being done is AI. So they don't believe whatever has been done is AI. So these people don't call this AI anymore. So what Deep Blue did was, Deep Blue was just able to compute much, much more, much faster than Kasparov could. But it wasn't really smart in that sense, right? Kismet, again, was an MIT bot which was able to emulate and respond to your emotions. So it could read your face, see you're sad, and then was able to empathize with you, right, a little bit. And then there were a few more toys like Aibo and Roomba products that actually used a little bit of AI. So it's not blue like the first one, but there were real products that were using rudimentary AI to deliver value. Right? So things happened, things moved, not very exciting, but at least they were getting productized. But something changed around 2011. And the first thing that happened was, again, it's not the first thing, but one of the interesting developments was Watson actually won Jeopardy. I don't know how many of you saw that, but it beat the best Jeopardy players and won that. Now, this may seem like a game, but it's a significant advancement for AI, right? 2012 was, again, a seminal year. Something happened in ImageNet. I'll talk about that in the next slide in more detail. But this was a super important moment in deep learning space. In 2014, you saw Hygene, which was Hygene and Alexa. So Hygene is interesting because it was that chatbot which won the Turing test, by the way. The 1950 challenge was actually won in 2000, was actually broken in 2014, not in 2000. So Alan Turing wasn't too far off. Now, essentially 33% of the time it could fool humans into believing that it was human if it chatted for 5 minutes. If it talked for 15 minutes, you could tell 100% of the time that was a bot, right? Now, this is symbolic again, just to give you a sense of how long does it take for things to fructify and deliver value. But Alexa leverages it, it's widely distributed. 2015, Google essentially open sourced TensorFlow, which is a deep learning library used in extremely sophisticated systems, but made available by Google to everybody. This triggered a barrage of innovation that happened, right? 2017, AlphaGo. How many of you have heard of AlphaGo? Okay. AlphaGo is an interesting thing developed by DeepMind, a Google company, which essentially beat the world Go champion. Go is a more complex game than chess, and it beat the world champion, right? This was, again, a seminal moment in AI. People were very happy. Then AlphaZero happened in the same year. AlphaZero was better than AlphaGo. It beat AlphaGo 100-0 in Go. And then it beat the best chess program that has beat all grandmasters in a 100-game match. But the interesting part wasn't just that. Not just that it beat something. It did so without training on any data whatsoever. So AlphaZero essentially was only told the rules of chess. It was not fed any data. It played itself 4 million times and became the best chess-playing entity in the history of mankind, or universe, right? So the grandmaster, you should watch if you can, right? Some of the grandmasters reacting to AlphaZero's victories, and it's amazing. And then there's something called Capsule. I won't delve into that. We can dig deeper. But essentially, Capsule tries to eliminate the need for data. So the example a good friend of mine who's an expert gave me was that as human beings, we don't need 3 million miles of training to become good drivers. We just drive for a few, less than 100 miles, and become good drivers. Google's autonomous car requires 3 million miles of training and still hasn't become as good, right? Now that's key, right? So the Capsule essentially allows you, or has the promise that you won't need as much data to become intelligent, right? And 2018, you're seeing AI chips, which means your fundamental instruction set will move to AI level, right? And that's being funded. So So there's a lot that has happened in the last decade or so. If there's one key takeaway or a few key takeaways, first of all, the acceleration in this is unprecedented. The ubiquity of this, or the breadth of distribution, is again unprecedented. It's across companies, across domains. Stuff is getting over open source every day, right? And you are actually seeing a huge impact coming in. Now, I talked about ImageNet. This is an interesting thing which highlights one more point that I wanted to make. ImageNet is a competition where you have a large database of images and you write algorithms to see if you can recognize objects in those images, right? In 2012, something important happened. There was one group led by Jeffrey Hinton from University of Toronto that actually beat the previous records by 10 percentage points. This was a technical accomplishment, that was amazing for the research community. So that was super important. They used deep learning, a form called CNN, convolution neural networks. Very good. But what's interesting is from 2012 to 2017, in 5 years, not only did state of art become so good that it's better than human performance, so these algorithms do better than you when they have to detect objects in a picture, right? Or you and I, no offense to you, all of us, right? But the second important thing is that if you notice 2017, 29 out of 38 teams did better than human performance. So it's not like one community in one company is doing it. This is a broad-based technology that everybody is able to use. This is pretty unique, right? This last one, I won't dig too much into it, but it's not just about games, right? Games are just a way to train easy to get data on develop algorithms. But Stanford researchers, I think it was January of this year, they actually developed an algorithm that can do better than your dermatologist, right? And this is pretty sophisticated stuff. Now, some other technical accomplishment that give you a sense of how good we are getting, right? I talked about object detection already. It is a given that algorithms will beat us any day. Question answering, right? This is if you give me a document or you or I a document and you were to read it, and if I were to ask you some questions on that document, you'll have a certain performance. If you were to give it to an algorithm, it will answer those questions based on that document. It's getting, we are still better, so we are still better than computers here, but it's getting very, very close if you see the improvement that's happening. The last one is speech recognition. So they take phone audios and try to say how well does the algorithm do relative to that. It's achieved human level proficiency, right? So you might find it hard to understand what I'm saying, but the algorithm would not, right, most likely. Right? So it's getting there. Now, is it all great? I mean, is it really great? So that is all the good side. Now, it's actually not. What we've seen is narrow AI applications. We are able to make dramatic progress. Now, this is an example of a problem that AI is struggling to get close to human performance. Now, what is this? If I were to give you a picture and ask you questions about that image, right? Oh, is the chair to the right of the dog or to the left of the dog and things like that? Humans are incredibly good at answering that. The algorithms still are struggling to do that. This just tells us that generalized AI is still far away, right? Now, there are people like Elon Musk who arguably know much more about things that are not publicly declared, right, publicly known. So they have a much more drastic position. But if you take Elon Musk out of picture, I think this is generally agreed upon view that narrow AI has a lot of promise. Generalized AI is still further away, right? And this should help set expectations on what we believe AI can do for us from a security perspective, right? So why has all this change happened very quickly? Why are we not like the 50s and the 60s? First of all, the amount of data, all these algorithms are data hungry. We just didn't have this kind of data in the 60s. So lots of data. Compute was supremely expensive. Now compute is easily available. It's extremely flexible computing infrastructure. You can use it, reuse it, distribute stuff around, and it works. There are use cases like search and social media that are have a lot of money. So companies like Facebook and Google are able to plow their profits back into a lot of AI research. And all this has fueled algorithmic innovations. Just to give you a sense of mathematics being done here, there's math that has happened over the last 150 years that was not put to use in any dramatic way, but AI actually is leveraging a lot of this. So it's almost like there's a pipeline of work that had already happened, which was waiting to be used, and now it's getting used for AI. So there are people now who are modifying those things, making it better for AI purposes, right? So you will continue to see a lot of work happening in this. Now let's get to the problem at hand for us, right? So I just laid this out to give a sense of, is it just going to solve everything for us or not? I don't think it will. Now applying AI to chasing bad, which is what my original premise, right? Chasing bad is an unbounded problem. There are three things that make it really hard to solve chasing bad using AI. The first one is that if you look at the problems AI has solved, like chess, you have an adversary, but there are rules that the adversary has to follow, right? On the other hand, if you talk about self-driving cars, it doesn't have any clear-cut rules, but usually you don't have adversaries in self-driving cars. It's not like people are trying to drive into you, right? It doesn't happen. Or user is not deliberately trying to cause an accident. There are exceptions, but that's not the primary way it happens. But cybersecurity or chasing bad, you actually have adversaries, and they're definitely going to break rules. They have no rules they follow. And the last thing that makes this really difficult is data scarcity. You need to know about a lot of bad data to be able to learn. Now, the newer algorithms we have, like deep learning, are extremely data hungry. They just need millions and millions of data points. So you need data on millions of attacks to be fed into these engines for them to train. It's just not available that easily. So it's really hard for AI to solve this problem. So yeah, I mean, if somebody claims they have solved this, I think it's worth investigating, right? On the other hand, what about ensuring good, right? This is where we believe, and we have actually seen work that allows us to solve this, right? So first and foremost, it's actually a must. When you're trying to achieve cyber hygiene, if you were to manually or based on rules trying to achieve cyber hygiene, it's too large and too dynamic an environment. Right? On the other hand, if you had to understand the composition of an application, it can be solved using a combination of rules and AI. What I mean by that is every application on a virtual machine or a server has a set of binaries that run on it to deliver a particular role, right? But that's not, let's say, an Apache web server. But that's not the only instance that we have, in our data center. So you know that roughly the set of binaries that are here would be the same as another instance. If they are very, very vastly different, there's something going on, right? So we can use, and these are not rule-based again, right? These are things that you can learn from based on data that is given. So application composition is something that we can understand using AI. We've done research on this, and it works in our products. Application behavior. Now, if you look at Windows processes, there are numerous processes like LSAS and SVC hosts, which are used by attackers to compromise machines every day. Those all behave in a predictable way across instances. Now, I'm not saying they behave in one way. They behave in a predictable way, right? And you can learn the intended behavior of an application by actually learning from a large amount of data. And if you see an anomaly, because you can learn, then you can also detect anomalies, right, from that intended state. And last thing when you're trying to do cyber hygiene is that there are changes that are made day to day based on your operations. You go and patch your systems. You go and change the network IP addresses, network configuration. All those changes, if you're not able to handle, will create false alarms, right? So what you need to be able to do is you can leverage AI again to understand those changes and automatically classify them as expected changes. So again, at no point in time here do you try to understand or do you have dependence on bad guys. It's just about understanding our own home, organizing our own home, right? This is not data scarce. So solving this is not adversarial at all. All you're doing is trying to figure out, is my house ordered in the best practice way or not, right? This is not an adversary coming into you. It has rules, because for applications to function properly, they have to follow certain rules, right? And there is data. So we, as VMware, we have applications running on 65 million virtual machines. We can get, we have access to that data. I mean, when I say we, I mean collectively VMware and customers have access to that data. So this problem is much more solvable, right, using AI/ML. And what more can we do with AI? Is it that just you can ensure cyber hygiene, or can it actually help with security operations beyond just ensuring cyber hygiene? So I put the Jarvis quote thing there because I don't know how many of you have seen Iron Man or aware of Jarvis. Yeah, so yeah, I think Jarvis is just a rather very intelligent system. So it kind of augments Iron Man, provides him contextual information all the time wherever he is, right? So I think that's a job that AI can do for security operations. So imagine a security analyst. Every time an alarm comes, they spend most of their time trying to understand the context within which that virtual machine is playing, what happened before, what happened afterwards. Are there other VMs that have seen a similar behavior? They can't answer those questions. They have to go and investigate it over days and months. All this can be automated, and this can be provided at the tip of the fingers right away. The second thing you can do is that every alarm that comes in usually requires a decision making again, right? You have to do extra analysis on it. Now, AI can essentially think of AI as, or Jarvis, whatever name you might give it, to actually do a deeper analysis on the specific VMs or specific applications that you suspect have an event that's worthy, right? Now the challenge is, if you were to do this on every virtual machine all the time, there's a cost to be paid, right? You will actually, there's a CPU cost on the workloads on which you're running. Plus you will start generating alarms. But on the other hand, if you were to just use it selectively for machines that actually you suspect have something going on. So it's like an under observation mode, but instead of a manual security analyst observing it, Jarvis or whatever the name you might want to give can do that, right? So these are things that you would continue to see security operations centers and software, to evolve into. So those are some of the ways that that you would see this develop. Now, in a nutshell, right? The way to think about how this will get solved is you should organize, or we believe you should organize your SOC tools into two groups: tools that ensure cyber hygiene, and that should be the primary focus, because that is a bounded problem. That is the problem that handles most of the risk. It's a risk-based approach. And then have a set of tools that address the residual threat, that actually can leverage the application context provided by the layer beneath it, right? So if there are three things that I want you to take away, and you can ignore the AI history, you can ignore everything else, but if there are three things I want you to take away, the first is focus on cyber hygiene, right? We talk about threats too much. It just feels cool, but it's extremely hard to tame them, right? The second thing we should do is leverage virtualization or a layer like that to achieve cyber hygiene and automation. Because there is this layer which maps what's in the app layer and what's in the infrastructure layer. You should be able to leverage that. So you should ask that question of your vendors and everyone, how can I leverage it? Most often when people talk about virtualization, the question they ask is, how secure is your virtualization? I think that's a good question, but a better question would be, how can I use virtualization to secure my environment, right? So you have to use virtualization as a tool to do it. And the last one is that you should ask your vendors to leverage AI and ML to achieve cyber hygiene. A lot of them would talk about using AI ML to detect cyber threats. that is, while that is, something that's commendable, I think it is likely to hit diminishing returns given the state of where AI is and the nature of the problem we are trying to solve. On the other hand, this problem is a much more bounded problem, and AI/ML can achieve significant improvement in your efficiency, in your security operations efficiency. Okay? With that, I'll end my talk. Thank you.